Let's start our first example of optimization, and I have the 4 steps there from our handout appearing. I'm actually going to move this up so we can see the statement of the problem by itself. Exercise 1, concert promoters have determined that they will sell 2,000 tickets if the price of a ticket is set at $40. For each $1 increase in the price of a ticket, the promoters expect to sell 20 fewer tickets. What ticket price will bring maximum revenue from ticket sales for the concert? What is the corresponding maximum revenue? So in this problem, we're selling tickets for a concert. We're trying to determine what price to set the tickets at. And somehow there's been market research done where you know that if you set a higher price, fewer people will attend the concert. So if the ticket price is too high, you'll have so few people, you don't make much money. Of course, the cheaper the ticket, the more people come. But if the price is so cheap, you might have lots of people attending a concert but still not make much money. Does that make sense? So we're going to start going through my 4 steps here, where step 1 is a crucial step where we have to identify the function we want to maximize. So let's just write identify function to maximize. And that here, the function we want to maximize is the money we're going to make from the sale of tickets. Whoops, slid up too far. And so how do you describe the money that you're going to make from the sale of tickets? Well, it's not that's not complicated. It's how many tickets you sell times the price per ticket. So eventually we're going to settle on just one price per ticket. There's not going to be different price tickets. They'll all be the same price. So maybe to have some variables here, I'm just going to say let x equal the price per ticket, and I'm going to let n equal the number of tickets sold. So then our amount of money we make, I'm going to call that the revenue, is going to be equal to the number of tickets sold times the price per ticket. So in my symbols here, I might write R for revenue too. So I have R equals N times X. The revenue is what we want to maximize. Maximize the revenue. So that's the function we want to set up in the end. We're going to focus on working with this. It's a fairly simple expression here, just n times x. Now the problem is we got too many variables. We got an r and an n and an x. I want just one variable on the right-hand side of this equation. So that's where step 2 comes into play. We're going to find a relationship between n and x in this problem. Now, in the statement of the problem, we see that we'll sell 2,000 tickets if the price is set at $40 per ticket. Let's go ahead and actually, I'm going to set up like a table of values here, X in N. So if we set the price of a ticket at $40 per ticket, we're going to sell 2,000 tickets. And then the wording of the problem says for each $1 increase in price, we expect to sell 20 fewer tickets. So if I increase the price of a ticket by $1, I expect to sell 20 fewer tickets, and that's going to be 1,980 tickets, right, that I'm going to sell. So that relationship between X and N is a linear relationship. Because if I added another dollar increase, the value of N would go down by 20 tickets. It's like we have a constant rate of change here. We've talked about constant rate of change earlier. And if there's a linear relationship between X and N, now I'm going to draw just a very rough sketch of a picture. Like we could have an x-axis and an n. N is kind of like y here. At $40, we sell 2,000 tickets. But at $41, we're going to sell fewer, right? 1980. So there's actually a straight line that would pass through all the points that give the relationship between the ticket price and the number of tickets sold. So what's the slope of this line? Or what's the equation of this line? Now I'm thinking y equals mx plus b. But I'm actually going to write n equal mx plus b because we have variables n and x, right? So the slope, m, is going to be change in output per change in input, change in n over change in x. I could just subtract 1980 minus 2,000. Now I got to be consistent. 1980 goes with $41, 2,000 goes with 40, and I'm going to get negative 20 over 1, or negative 20 is the slope for this linear relationship. The line is decreasing as we move from left to right, so we expect negative slope. And this negative 20 that we're getting for slope just reflects that 20 fewer tickets for each dollar increase in price. So we got, okay, so n is equal to negative 20x plus b, but we need a b value. So I'm just going to plug in a value of x and n from my table. Doesn't matter which ones. I could plug in n equals 2,000 equals negative 20 x equals 40 plus b, just like you would with the equation of a line, to solve for the b value. I'm not actually going to go all the way over to where the y-intercept is. So we have 2,000 equals, this is negative 800 plus b, or 2,800 equals b. Okay? So what this means is we have this relationship n equals negative 20x plus 2,800. That's our key, and I know that's quite intense, right, finding that. That's our key to step 2 because that's a relationship between n and x. Now we're ready for step 3. That's our constraint, by the way. We call that a constraint on this problem. Now let's go to step 3. What we want to do is we need to step 3 says solve for a variable in the constraint equation, then substitute into the function from step 1. Well, we already have n solved for. So now for step 3, I'm going to take my function r equals nx, the revenue function. That's what we want to maximize. That's the function we want to set up. And I'm going to replace n with negative 20x plus 2,800. So this tells me the substitution I can make for n. Negative 20x plus 2,800 is equal to n. I still have times x on the end, right? I'm just substituting in for n. And when I distribute here, I get r is equal to negative 20x squared plus 2,800x. R of x is a quadratic function. So here is our quadratic function. That we want to find our maximum value for. And really, getting to this point is the hardest part of the problem. So I'm going to recopy r of x here on a separate sheet of paper. Now, we know the shape of the graph is going to be overturned U-shape because our a value is negative on the quadratic function. So we know the vertex is a maximum point. And that's where the most revenue is going to occur. And you could even imagine a graph where x, r of x is the revenue, x is the price per ticket. We're going to have this overturned parabola, and so we're trying to find the maximum revenue for this function. So let's find the coordinates of the vertex. Vertex. The x-coordinate is negative b over 2a. Now, I already said a up above here was negative 20. We also have b equals 2,800, right? Because here's our expression for the quadratic function. So negative b over 2a is negative 2,800 over 2 times negative 20. That's negative 2,800 over negative 40. When I divide that out, I get 70. So the maximum revenue occurs when X is equal to $70. That's the price per ticket. And I think, let's see, we were asked what ticket price will bring in the maximum revenue. That's one part of the answer to this problem. We also need to evaluate R of 70, because we want to know what the corresponding maximum revenue is. How much money are we actually making? And that's negative 20 times 70 squared plus 2,800 times 70. I'm just plugging into the quadratic function, and I get $98,000. And so the corresponding maximum revenue is $98,000. No matter what price, except for the tickets, you can't make more than $98,000. So on our graph, this vertex point where horizontal axis is X, vertical is revenue. These are both dollar amounts. This point is 70, 98,000. And in this picture, we don't have the number of tickets sold. We could figure that out if we wanted, but I'm just answering the question in the word problem. They want to know what ticket price will bring in maximum revenue. The ticket price is $70 per ticket, and the corresponding maximum revenue is $98,000. Extra, if you're just wondering how many tickets are being sold, you can use that n equals negative 20x plus 2,800. N is equal to negative 20 times 70 plus 2,800. And I believe, and that's going to come out to be 1,400 tickets. But they didn't actually ask us for that, so I'm not going to put that in a box. And that doesn't appear on this graph. So what happens if we charge more per ticket than $70, the number of tickets drops off somehow, so we make less money. If we charge less per ticket, maybe we get more people, sell more tickets, but we still make less revenue because that vertex is the high point, highest possible revenue for this function. So I just want to show that there was our revenue function, and there's our final answer to this problem. Good problem.